export to cloud. I don't have any huge overall announcements today from myself. Shawn, do you have anything you want to talk about?
I don't think so. No, that was my small talk for the morning, was the news.
Fair enough. All right. So today we have two different topics coming up. First off, we have a PyGS intro from Yu-Chen. And then afterwards, Russell's going to give us a bit of a pysat and OMMBV overview. So, Yu-Chen, are you ready?
Yeah, I'm here.
Awesome. Well, you have the floor.
Can you see my screen?
Yep.
Okay, good. This is Yu Chen. I am a research scientist in Center for Space Plasma and Aerodynamic Research at the University of Alabama in Huntsville. Today I will be introducing our PyGS package, which has been published on PyHC website recently. The PyGS is comprehensive tools for small-scale magnetic flux ropes based on the GarageBand reconstruction method. And this project is supported by NASA grants. Here is my outline. I will first introduce what a magnetic flux rope is, and especially for the small scale ones, and why we care. The techniques we use is based on the GarageBand technique method. So I will briefly cover the reconstruction and detection, as well as their developments. And finally, I will show you guys what our PyGS package can do and how it works. So what is magnetic flux rope? I have four figures to introduce this structure. The left one is a schematic of interplanetary coronal mass ejection. The ICME flux rope is also known as magnetic cloud. And in our community, it is actually the large zero flux rope and described by this purple helical field lines. The scale size is usually greater than 0.1 U, and the duration is about several hours to days. There also exists a small-scale magnetic flux rope, whose duration is only several minutes to hours. This terminology was first mentioned in Moldwing et al. In 1995. The second figure is 1D time series plot via the in situ spacecraft measurement. Both magnetic cloud and small flux rope have bipolar field rotation in at least one field component. For example, on the first panel, we can see BZ changes from positive to negative, while BX and BY remain negative and positive respectively. The second two fourth panels are plasma bulk properties and alpha to proton number density ratio. Magnetic cloud usually has significant change in, is anything wrong?
No, okay.
Oh, okay, I'm still online, okay, yeah. The magnetic cloud usually has significant change in plasma number density and plasma beta, while for the small flux ropes, based on our database, we didn't find any uniform change in these structures. The magnetic cloud also has a very high number density ratio. The last panel is electron pitch angle distribution. For magnetic cloud, it often has counter-streaming electrons or bidirectional signatures on the EPAD panel. The situation for small flux rope is pretty complicated. Some events may also have this bidirectional electrons, while some only have unidirectional signature, just like this one. And some events don't have any significant changes on the EPAD. The third figure is 2D cross-section. By the way, these two are the same event. On this 2D map, we can see there are closed field line regions, these black contours, and the gradient of unipolar axial field represented by this color bar. The 2D flux rope is also known as magnetic island. The last figure is 3D field configuration. On this figure, we can see both events have magnetic field lines twisted around the central axis. These two are actually outputs of the gas reconstruction. Why we care about the small flux rope? The major reason is that compared with magnetic cloud that is from the sun, the source of small flux rope is still inconclusive, which is an important open question. In earlier research, small flux rope were suggested to be from solar eruptions, just like small CMEs. Later theoretical simulation and observational evidence all support that these structures can be formed locally via the MHD turbulence. Recently, we found that the interchange reconnection can also be the mechanism to form these structures in the low corona. The second reason is that these structures have pretty unclear evolution since the scale is too small, much smaller than the separation between two or multiple spacecraft. Therefore, tracking individual events over distances is quite challenging. In the meanwhile, we found these structures can occur overlapping with the other dynamic structures, such as torsional up-and waves, magnetic switchbacks, etc. Based on our PSP observation and the current limitation of the single spacecraft environment, we figured that it may be better to broaden the current definition of the small flux groups by including both traditionally defined quasi-static structures with those structures have a significant field flow. The third reason is that the role of small flux groups in particle acceleration and energization has been extensively studied. This process is sometimes through the merging of multiple flux groups, which can directly accelerate particles by reconnection electric field, or particles will be trapped within closed field regions. As I mentioned, the PyGS is made for the JS-based techniques, which actually relies on the idea of the JS reconstruction. Speaking of this reconstruction, we need to go back to the JS equation, which is this formula. Here, PT is transverse pressure, the sum of thermal pressure and axial magnetic pressure, and A is magnetic flux function or vector potential. This equation indicates that PT is a single variable function of A. By solving the JS equation, we can obtain this 2D magnetic field configuration. This is done by first, the right-hand side of the JS equation, both PT and A can be calculated along the spacecraft path. Then by solving spatial initial value problem, we can get this A values over the 2D scale. In summary, this reconstruction can recover 2D structures, this part, from 1D in situ spacecraft data. We usually mention this technique is 2D, but actually it is 2.5D. The 2D is on the cross section, and for each cross section, there is one corresponding z-axis. The JS reconstruction is needs the optimal z-axis. That is this 0.5D comes from. The idea of the JS reconstruction was from the Sonar and Guo in 1996 and Hall and Sonar in 1999. And after that, it was developed into different research areas. For example, Hasegawa used this JS reconstruction, developed the MHD reconstruction, which was mainly applied to magnetospheric and magnetopulse research. Tai mainly works on the JS type equation, which is more a general form. The application to magnetic flux group was created by Hu and Sonar in 2001. The program is MATLAB-based. Here are some scientific highlights and selected outputs. As aforementioned, the technique can provide 2D cross-sectional maps of coherent structures and 3D field line configuration, just like what I showed in the flux group introduction. It can be applied to both magnetic cloud and small flux groups. For flux group parameters, it can provide axial current density, scale size, and some estimated parameters, such as toroidal and phoidal magnetic flux, relative helicity, and average twist, etc. The JS technique also includes several useful functions, such as a Wallen test, MVB, frame analysis, etc. It was recently applied to the extended JS equation, and thus it can be applied to broadly defined flux groups. In our PyGS package, we migrate the MATLAB-based code to Python 3 and make it to be open source with several new functions and updates. Please notice that the 3D features not included in this PyGS package yet. And also I have a star regarding these several new functions. This is because during these 20 years, Dr. Hu shared his codes with the other teams, but we are uncertain which version they have. The second product is the JS-based detection, which relies on the idea of the JS reconstruction. The left schematic shows the core signature of the detection algorithm. These are 2D cross-section. The view is from the axis. These colorful contours represent isosurfaces of A. Imagine a situation that spacecraft traverses a flux rope. It will start from this dark blue curve to the purple turning point, then from this point to the blue curve again. In other words, it will collect data across the same set of isosurfaces of A twice. Then along this spacecraft path, A will reach either maximum or minimum at one point. This point is also called turning point. Then at this point, we split the spacecraft path into two approximate branches, the first and second half. Each half path can be described by one PT versus A curve. Notice that the colors on the left and right hand sides are corresponding. So for the first half, it starts from dark blue to the purple turning point. The turning point is usually on the top, since flux rope will have very strong axial field in center. Then for the second half, it starts from purple triangle to the dark blue one. Remember that PT is a single variable function of A. It means that for each A value, there is one-to-one correspondence PT value. Then for a flux rope-like structure, one branch of PT versus A can fold onto the other. This is called double folding pattern in PDA. Then back to in situ data arrays, we can check if there is such a pattern. Here are some major steps of detection algorithm. The first step is pre-processing data, including magnetic field and plasma properties. The second step is searching flux rope candidates based on this core feature. Since flux rope has a wide range of duration, we use sliding windows to cover 9 minutes to 6 hours. The third step is post-processing. At this step, we apply a set of criteria to determine whether an event candidate can be called as flux rope. Then at last step, we calculate flux rope parameters and output results. The original JS-based detection was created and published by Jan Hu and Hu et al. In 2018, which was also available on Dr. Jan's GitHub. It supports the wind and ACE data sets, and it is Python 2 based and with associated package. Based on this detection, they created flux rope database by wind data set for 20 years, and they provided observational evidence for MHD turbulence generated scenario. This detection is more efficient than visual identification, and it can also identify those flux rope who have very weak rotations. This original detection applies to polystatic flux rope only, and this version doesn't include the thermal pressure. After 2018, Dr. Jen graduated and left academia. We took over the original detection code, but it has to be implemented via several scripts separately. And since he didn't make any advertisement on his code or his GitHub, I think that would be the major reason this code is meant for internal use. And by the time we submitted this proposal, I think we were still the only team using the JS detection. During these years, we also made our own developments. First, we applied the full JS equation by adding thermal pressure and make the electron data to be optional. We implement this detection to different spacecraft data sets, including 2 full missions. In the meanwhile, we add several functions and output parameters. It was recently extended to the general JS equation, and thus applied to broadly defined flux ropes. In our PyGS package, we migrate the most recent version to Python 3 with more compatible packages. We add one more spacecraft data set, the Solar Orbiter, and we also did further improvements, including streamlining several modules and reducing redundancy. I think it's time to officially introduce our PyGS package. It consists of 2 key products, the detection and reconstruction. The detection can automatically identify flux ropes, which is supporting statistical analysis. The JS instruction can visualize and categorize the 2D magnetic field configuration, which is useful for case studies. Both methods rely on the generalized JS equation and can be applied to broadly defined flux ropes. The current supported spacecraft data sets include PSP, so orbital Ulysses, ACE, and WIND. The beta version is not available on our GitHub or the PyHC website for public testing. It is Python 3 based, which needs several packages. The data downloading part is still via AI-CDS, SpacePy, and CDF library. The current supported installation is via setup. We have been thinking about the PEEP installation. The embarrassing thing is that our PyGS, this name has been occupied by the other Galaxy project. So that's why it is still to be determined. The third option is to run this PyGS package via script files without installation. I would say it may be better. This option may be better for those people who is familiar with file group structure, such that they can do their own improvements or modifications. Here is a coding example of the detection. The final outputs include event list and time series plot. To run the detection, users need to specify script ID, times of searching, and duration window. I have the duration 1030 as example here. It actually runs two windows, 1020 and 2030 for flux group detection, which means the upper limit for the flux group candidates would be 30 minutes. The electron data here are optional. Users can turn on both, or they can just turn on the include temperature, such that the electron number density will be replaced by proton number density. The rest controllers are independent modules. If someone would like to do the pre-processed data, they can just turn those off. And the searching part is most time-consuming process. If someone would like to redo the post-processing without searching, they can just turn it off. We also have a controller to load a file to remove those intervals containing shocks. This shock data file is from IP shock database. We also have one more controller to let people decide whether they want to have the overlapping intervals or not. Here are final outputs examples. The left one is time series plot. During this 4 hours interval, we have two events, both have clear bipolar field rotations. I would say there could be one or two more flux group around here, but the upper limit or the duration window limit is set to be 30 minutes. That could be the reason we missed this two events. The right figure is a screenshot of our final event list. It includes several parameters calculated within this interval and some special outputs via the JS technique. This is a coding example of the JS reconstruction. The final outputs include a set of figures characterizing flux group parameters. Since this reconstruction is a little bit complicated, we recommend users reading the instruction first to understand the interactive input. And also we have several information and guidelines, warnings on the terminal that's running via script file is preferred. Similarly, run this reconstruction, users need to specify the spacecraft ID first. For time of interval, there are two options. If reconstruct events from detection, then users need to specify the pico file and the event sequence number. The times of interval will be read from this pico file directly. And the second line is optional if they don't reconstruct event from detection. As I mentioned, although this is a 2D technique, we still need a flux group z-axis, and this controller indicates the source of axis. If users would like to adjust axis from detection, or they want to get the axis from reconstruction, they can turn it on. These two controllers are default grid points. Then the first row is default settings for round 2, which can be changed as needed. By the way, this reconstruction has to be run twice to get the final result. The last 4 rows are add-on features. They can be turned on if some features are necessary. Here are major outputs of the JS reconstruction. On the terminal, it shows some parameters for the current reconstruction and some results derived from this technique, which includes the toroidal, colloidal magnetic fluxes, relative heat density, average twist, etc. This is a 2D cross-sectional map. Again, we can see the closed field line region and gradient of unipolar BZ. We can also read some additional information from this figure. For example, the scale size of this event is about 50 times 10 to the minus 3 AU, which is 0.05. And the maximum BZ, according to this color bar, is around 7.3, 7.4. Actually, it was already printed on the terminal. And also the affinity of this interval is pretty low, which indicates which is indicated by this the relation between these two sets of vectors. The right figure is PT versus A curves. We can see that the double folding pattern is pretty clear. Then here are the other outputs, optional outputs or features. This one, all these figures will pop up after turning this adjust axis on. This one is recommended to do with initial settings. If either this controller is 1, then it will read saved axis directly. After turning this one on, the residual map will pop up first and has default black dot represent the minimum residual direction. And users can select any points within this contour, then they will see all these figures. This one is PT prime versus A prime in different directions. And this one is parameters on the spacecraft path. As I mentioned, the A will reach either maximum or minimum along the spacecraft path. And theoretically, the boundaries of A values should be very close. Then based on these three figures, users can decide whether the current selection of the axis is satisfied or not. Then if someone would like to see the hologram, they can turn this plot hologram to be true. And this hologram is in MBA frame. Subscripts represent minimum, intermediate, and maximum variance direction. And the direction of the magnetic field is very clear here. Then I have the other optional outputs. This one is distribution of the axial current density GZ, which is controlled by this plot GZ. This one is volume relation plot. This volume relation actually can imply the affinity of the current interval. If this one is low, then it means the current fluxor is static or quasi-static. Then the right one is traditional spacecraft time series plot. And if someone's really familiar with the fluxor signature, especially for this time series plot, they can turn this adjust interval on to reselect the current interval. Yeah, if this one is changed, then they have to go through all steps to have the new axis, and that's a new cross-sectional maps and PT versus A curve. We also have some information printed on the terminal. And that's it. Thanks for giving me this opportunity, and thank you all for your time and attention.
Thank you. Do we have any questions for the attend?
I actually have one real quick. Sorry, this is going back to the slide you had on the PyPI stuff, but did I catch you say that there was already a PyGS in there?
Mm-hmm.
Oh no. What is
so
the other PyGS that's published?
Well, we're not sure about that. When we submitted this proposal, we figured the PyGS would be the best name for our package. And after that, one of my colleagues tell me that there's the PyGS package is already there. And it's a different brand. That's why my GitHub website is pygsdr/PyGS.
Okay, gotcha. Okay, and then someone just linked us to the other one, so I can go check that out to see what that is. Huh.
Yeah, so yeah, we've been thinking maybe we have to ask Rainer if he agrees with that we can change our name to PyGSDR.
Yeah, that could be like, yeah, I see what you're saying.
Yeah.
Huh. Alrighty then. Well, good to know that's a thing. I think I might have to go back and fix something I've published in Docker because I think I might be pulling in your package with a pip install somewhere, and I bet I'm grabbing the wrong one now that I'm seeing this.
Um, yeah, you're grabbing the correct one, but it's not can be done via the pip installation. If straight, then it puts the wrong package.
Yep. No, in a Docker file I'd published somewhere with some PyHC packages, I just had a big pip install list and I had PyGS just listed in the requirements
Oh,
file. So
okay.
I bet that's wrong. Whoops.
Okay.
Okay. Good to know this now. Thank you for talking about it.
Yeah, thank you.
Angeline, I noticed you unmuted. Was it to ask a question? Nope.
No, sorry, that was Zoom acting up.
No worries, no worries. It looks like Sarah posted in the chat what the other PyGS links to Python Galaxy server. The more you know. Does anyone have any other questions? All right. Well, thank you again, Yu-Chen. So next up, Russell asked if he could give kind of a high-level overview of pysat, OM, and BV. So you have the floor whenever you are ready.
All right, thank you. Can you hear me?
Yep.
Awesome.
And
All right, so
this new Cosmic Studio logo that you're now debuting for me.
yeah, thank you. So yeah, I'm transitioning. I've started an LLC and I'm starting a new identity, Cosmic Studio. So it's going to be my my business to cover physics research and other things that I'm going to be doing. So thanks for that, pointing that out, Shawn. So some folks may remember a few weeks ago, the Geospace Dynamics Constellation team came and talked about, came to PyHC to talk about the mission. So as a result of that presentation, I sent that team an email saying, hey, software the pysat team and I produce would be actually perfect for GDC for that mission and for future missions. It's like, I'd like to talk to you all about it. And they suggested PyHC. So now here I am. So it's going to be a high-level overview of like pysat and mission processing with a bit of a GDC focus. Just due to time, I'm only going to talk about pysat instead of pysat and OMMBV. So just a quick agenda overview. I'm going to talk about pysat's design, motivation, and history. Cover some instrumentation applications, like space science instrumentation, mission applications, constellations, single satellites, CubeSats, things like that. Science applications, and then finishing up with features, future, and funding, 3 Fs. So design, motivation, and history. A good metaphor is actually music recording. So when music recording first started, you had to get everybody in a room, all the musicians in a room at once. And the technology was limited to 1 or 2 microphones at a time. Now, 1 microphone is actually a really good technique. It produces a very natural sound. It can be very accurate in the sense if you're in the room listening to the song being played, and then you go back and listen to the recording from a single microphone, especially with modern mics, it'll sound really good. The challenge is not so much that the 1 microphone is that you got to get everybody all together all at once, right? And if somebody messes up, right, you got to redo the recording. So the music industry was fundamentally changed when multi-track recording came along, which enabled close miking, or you can have 1 microphone per musician, and it changed the industry, right? So you could have, say, a drummer in New York lay down the drum track, and then a guitarist in LA lays down the guitar, followed by a vocalist who does lead vocals and the backup vocals and the harmonies. So you just completely shifted the place and the time, and it just really opened up a whole realm of possibilities. And the workflow that developed in the 60s and 70s, so like this recording console here is the deck that was used for Pink Floyd's Dark Side of the Moon. That recording workflow is the same that's in use today. Here's a more modern console, so it's all digital, but it's got the same stuff going on in there. And then you have digital software, which actually recreates that same workflow that was done in hardware. So we really need this kind of stability and versatility for science data analysis, and it's totally possible, and it's doable. So it's really, we have thousands of science instruments coming. We've had these big groups that we've assembled to deal with a few instruments on a single satellite. But now that we literally have things like Starlink and other satellites that have thousands of satellites in the constellations, if we try to take that same level of personnel and techniques and apply it to that many instruments, it's just not going to work. So instead of like many scientists and engineers for one instrument, we need to turn like the scientist into like this conductor here, or for the mission processing operator, needs to be like this conductor here, is able to manage a ton of instruments all at once and have the versatility to be like, oh, a little bit more cello or less violin, or even, more cowbell or something like that. So we need software, we need a foundation that actually transition to this future. And that's kind of the overall thing that pysat is trying to address. How do we deal with the coming flow of data and address it in ways that actually make sense and are dealable? So pysat has kind of grown up on previous missions. It started with CNOFs. It's had a lot of work for ICON and Cosmic 2. This is involved in processing for the ion velocity meter on there. Cosmic 2 is a constellation, so it has 6. So also got experience with CubeSat missions. It was part of the processing for the sorting mission. And there's actually a new mission that Jeff Cleansing has applied it to that I'm going to be talking a little bit today. So it's got a nice heritage. So, what can pysat do for instrumentation processing? Well, here's just a prototypical example of what pysat does. So I'm just going to go through this basic example because it covers the main interface to a data set, which is the instrument object. So we're going to start out, we're going to import some background packages. We're going to import pysat itself, and we're going to import pysat space weather, which provides data support for a variety of space weather indices. Pysat needs to understand what data and stuff it has. So we're going to set a directory in this demo example here for pysat to download data to. Pysat is kind of like it's built on the same type of principles as GarageBand and Logic Pro, the Apple software that does the digital music recording and things like that. So pysat is the main user interface, and it controls all the things that go on. The user tells pysat what to do, and then pysat will turn around and tell plugins, or these little mini programs, what to do. And the little mini programs are the things that actually provide the downloading or the loading or the processing, all kinds of different things like that. So we're going to register a group of these plugins that's collected into the package pysat space weather, and that's what this line is doing. And so we're going to register all these plugins with pysat so it knows that it exists and it's there to be used. And then we're going to instantiate the main interface to a single data set. It's called an instrument object. And here we're going to use data from the ACE satellite, from SweepHam instrument. We're looking at historic data. That gives us the ACE object, which is the pysat instrument. And I'm going to invoke the download method on that object. So if you want to download data for any of the instruments, it's the same thing, right? You provide the range of dates, and then we're going to load the data. Here we go. And then we're just going to iterate through variables for this time range and plot it. And I've just picked out a couple here. So you can see just from this, we have a list of variables attached to the object, right? So because it's object oriented, there's a lot of helpful functions and information attached to it so that scientists and engineers have all the information that they need to do whatever task they need to do right then. You can see we've got a .meta, so the object also tracks metadata as well. Need to know about, the data that we're working with. Here shows a little bit of data access. We're picking out a particular time range, and we're picking out the variable over the iteration list. So we're selecting out a variable. In this case, pysat's using a data frame. The pandas data frame is the underlying data format. So this pops out just one of those series. So we can invoke the plot method on there and produces all these nice labeled and formatted plots. Okay. So that's the general thing. Is the instrument is object, as I said, is the interface for scientists and engineers into the data, into whole kinds of data sets. And we can build upon this to create instrument processing. So this is the latest example. It's from Jeff Cleansing, who's an NASA employee. And he's using it for this new mission Reach, which apparently has a bunch of instruments on a commercial constellation, right? So what he's doing here, starting out for this 4 inst ID and arrow reach IIDs, this is actual little code for processing the mission. This is, I just took screen captures here. So this is iterating over all the different satellites within the constellation. So for each different satellite, it's going to instantiate the instrument, right? We're looking at level 1B data, so you can access different levels of data within a single support module. And then he's going to iterate over all dates within that instrument, and he's going to load the data. So when he loads the data, all kinds of stuff happens, because it's not just the simple, it's not that pysat just simply loads it and then presents it to the user. It engages a whole chain of functions. And these whole chain of functions makes the instrument object very dynamic. And it means you can, as like say user A, attach things that you say, this stuff needs to happen to the data. And then you can pass that thing off to somebody else and it's still going to happen, and they don't need to know or understand or anything like that. So it allows all kinds of processing. So there's a lot going on in this flow. So what happens is we've defined an instrument here, a user's defined one, these inputs map into different parts of this data flow. If a user comes along and says, give me a .load, then pysat's going to go to the files, figure out which files it actually needs to load. It'll pass that information to a load function that's provided by the plugin, and the plugin will then actually load the data. It's going to go into what's called the pre-process function. So this is also provided by the plugin, and it allows the developers a chance, immediately as the data comes off the disk, what kind of stuff needs to happen to it before the user needs to see it. So there's all kinds of challenges with mission processing, and you're going to set up a system at the beginning, but then after launch and things like that, it may not be exactly as expected. So this pre-process function can be quite useful. From there, it's going to go to a clean function. So we've all encountered, you have measurements from an instrument. All those measurements aren't necessarily going to be equally good. Sometimes the satellite's in more challenging conditions. And historically, what has happened, if there's a paper on the instrument or on the data release, is that the team provides cleaning parameters or notes like, here's how you get to good data. But then it's incumbent upon users then to actually implement that correctly to get good data. By including this within pysat, the clean function, it allows developers or the people on the mission instrument team to directly put those types of selection criteria into software. So a user comes along, they can just hit load. The different cleanings will be applied as they specify good cleaning, medium cleaning, that type of thing. But then it's actually make sure it's done correctly, because it offers the actual instrument team an opportunity to supply those parameters. I'm going to skip this pad data for right now, and then it's also got a nano kernel. So this is a small kernel that applies a series of functions in the provided order. So as a developer, here, if I go back here, I can attach a series of functions to this instrument object that will get applied to the data when it's loaded and before it's presented to the user. So you can use this functionality here to apply all the different processing steps, that you're going to need for the instrument, whether that's calling Python code specifically written for the instrument, or maybe it's calling some external packages. Maybe it's even interfacing with an IDL or MATLAB routine or something else provided by the instrument team. But you can use this to arbitrarily modify the data in a systematic way. So it encourages good design from the instrument team, and it just makes it easier on developers to create even very complicated processing type of situation or environments in a way that's as simple as possible. All right. So even though I went back too far. So even though this is only a few lines, all right, we've created an instrument object, we're iterating over the dates in the instrument object, and then we're loading it. This is the prototypical example, really, of instrument processing. You can arbitrarily go from the L1B data to the L2, which is going to be like the science ready type of things. And importantly for that, you need to create files for SPDF or whatever the other relevant agency is going to be at the time to serve data from your mission, right? And I've been on multiple teams, and that usually takes a lot of time and effort. That was also true for the ICON mission. So on the ICON mission, a very compatible file format was created. And at first, I'd written the software for the IVM. It had a certain metadata standard. Later on, the team defined one, and that would require me to go back through the code and update all those terms to be, compatible with the new standard. And I have to admit, I didn't want to do that. So rather than go through and do that kind of, just update things, I decided, why don't I write software to do all that for me so I don't have to go back and do it manually, right? But the good news is now it's provided features within pysat that will apply for any mission. So you can, Jeff here is loading up files that are coming from the constellation, right? And they come in their just own native format, and it's not appropriate for him to just dump those into SPDF. They need to be in the right format to be consistent with everything else, so that it's easy for the public and scientists to incorporate it, right? So he's converting from that default kind of metadata standard to one that actually works as SPDF with just this dictionary that he's defined here. And you can see he's taken the content of name, the variable name, and he's mapping it here to multiple categories that SPDF requires: cat description, label access, field name. So this is just one of the techniques that you can use, but PySat is really built to make it very, very simple to go from whatever data format metadata standard you have now to whatever standard you need to get to. So that's going to saves people a lot of time and energy, which it's normally a big part of the instrument file processing. Okay, so that's instrumentation. What about missions? Because missions are more than just you have an instrument on a spacecraft, right? Well, usually you have to first usually write a proposal, right? So you need to define an orbit, identify science targets, probably. Then you need to fly your spacecraft through models of the atmosphere or the ionosphere to figure out what environment you're really in. And then you can take those parameters and provide them to an instrumentation model, so you can simulate instrument performance and things like that. And if that's not done at the proposal level, it certainly has to be done typically in a mission parameter thing. After you get selected, then you really have to prove that the mission is going to work and it's going to close the science. So there's a whole host of technologies that you need to bring together so you can get that information. And it can usually be quite a challenge. Well, PySat has developed an entire ecosystem here. So, and this ecosystem supports that specific challenge and actually more. So like I said, PySat is kind of like GarageBand or Logic Pro. It's like the central user interface. And then there's a number of packages here that are to the right, starting with like PySat models down to this PySat Space Weather. These are plugin packages mostly. So like PySat Space Weather, which is the package I was showing earlier, and includes a variety of space weather parameters like F10.7 and solar wind speeds and things like that. And that comes from different institutions and different spacecraft and other things like that. But it's all collected here. PySat Madrigal provides data plugins for all the data sets at the NSF Madrigal database. So you don't need to go and learn PySat Madrigal, because PySat Madrigal works through PySat as a user. You just go to PySat and you say, hey, I want this data set. And when it actually happens to come from this package and is registered, then these routines get used by PySat to provide the user with the data and the information that they need. And the same way, we've got packages for PySat CDEC and PySat NASA. Right, so there's a whole bunch of different NASA instruments that we already support, and you can access all of that through PySat in the same way as any of the other ones, and it could include, GDC and other things coming up. PySat Models is also a plugin package, and that it provides access to model data, but it's like a plugin package plus, because it also includes a variety of analytical and other types of tools to work with model data, right? So model data is a little different in ways than spacecraft data can be. So the functionality is, conveniently located in that package when it's close to the models. The point being, for something like developing a mission, we've got this PySat missions package, which is couples to like an orbit propagator. So you can say, hey, PySat, I want to simulate an orbit, and you can use the data sets or the generated data sets over here. You can put in the orbit terms that you want. It's going to physically, model that orbit and then propagate it forward in time. So you can define your orbit parameters for the mission. It'll give you the locations. Then you can go and then use the coupling provided by PySat models, take those simulated locations to pick out, say, a simulated atmosphere ionosphere that's provided by PySat models. Now you've actually got the ionospheric parameters, and you can use again the pysat versatility to then pass that over to an instrumentation modeler that's developed for the mission. And now you're simulating instrument outputs, right? And now you can figure out how accurate the mission is going to be and what kind of science closure that you can perform. So I went through that whole chain for Icon and Cosmic too, right? We flew these things through models. And then, I had to provide the description of how IVM was going to perform and actually what those outputs would look like, right? So we've got a whole suite of tools here to provide that with pysat. And then actually, once you have, say, all those simulation things like that, you want to aggregate them together, you can use a tool like pysat seasons, which accepts any instrument or constellation object from pysat. I'll talk about constellations later, but we'll take any of those and it'll bin average them in a season. So it'll be, provide the type of science analysis that's been done for thousands and thousands of science papers. So it becomes a whole integrated system that can provide, make it easier for the team to get things done. All right. Just as an example of this type of workflow, I was just talking through it before, but starting with pysat 3, you may want to generate a TiGCM model of the ionosphere and the atmosphere. So you can use pysat and pysat like space weather functionality to pull out, hey, what's the relevant space environment looking at for the time we're modeling. You can use a pysat NASA to maybe get some other data to seed that model to figure out exactly what conditions you need. Once you get all of that together, then you can, use this whole pysat process to create settings for TiGCM. You run the model, you get output files. Now you can use the pysat models functionality via pysat to load up TiGCM and actually do model data comparisons or whatever type of things you want to do, run the drift model validation or density, temperature, all four, or whatever, So there's a whole lot of possibilities where pysat brings all these different type of packages together. Now, in this case, we're just showing pretty much powered by pysat packages plus TiGCM, but it works with any other software that you're working, any kind of package that you can talk to or couple with Python, which, should be pretty much anything. Here's an example just from the mission planning of one of those simulated orbits. So this example is effectively just like that prototypical example I showed at the beginning, which is why I showed it. I do define this dictionary orbit info, which says, hey, for the pysat orbit iterator, it's got a built-in real-time iterator, which can identify orbit breaks and things like that and just present to you data and orbit chunks. So I'm telling pysat here how to define an orbit or how to find one from the data. You need to define a pysat instrument just like you would any of the other ones. In this case, the platform is missions coming from pysat missions, and the orbit propagator is SGP4. Give it orbit properties. We attach this a calculation of solar local time to it. So this is that custom functions things I mentioned before. So now whenever this instrument is loaded in this call, it's going to simulate an orbit. After it defines all of those, then this calculate solar local time function is going to be applied to the object, and it's going to add a solar local time variable for us. And then I plot. That's not the plot that I showed. I'm showing this plot down. This other one here is actually over local time. So this is the full, I'm sorry, here's solar local time. So here's the full day universal time. Here's a solar local time variable. So we can see we've added solar local time to this orbit simulation, which wasn't there originally. We've got a full day. And you can see at the beginning of the day is not really the beginning of an orbit, where I've defined the beginning of the orbit as 0 solar local time. So in this case, when I'm using this this loop here is for I orbit inst and enumerate inst.orbits. This is inst.orbits. This is the real-time orbit iterator that I'm talking about. So it's just built right into a for loop. So each loop here, you're going to have just a single orbit nugget in the data. And this is showing a plot from one of those single nuggets. So you can see this was actually at the start of the day. So this is January 2nd. That's the day I loaded. But when it was started the orbits, it looked at that first chunk of orbit and said, hey, this doesn't actually look like a complete orbit. Let me load the day before, and look at that data and see if it's right or not. So it loads the day before, which actually then simulates the appropriate orbit for January 1st. pysat looked at that data and said, oh yeah, this chunk here belongs in this first orbit. So this is the first orbit that comes out. So it'll span day or file or month breaks or whatever, right? It's a very kind of useful and data-centric view. You can chunk or parse data from pysat that's independent of how the files are actually stored. So that's actually truly useful. So for like orbit iterations, or if you say have a bunch of level 0 files that are come down, say by telemetry, so it's in maybe random chunks or whatever, it's not all nicely chunked into maybe a full day file. Well, you can just engage an option in pysat to say, hey, data is spread out over multiple files, and pysat will take care of that and load multiple files for you in the background, and put together complete days. And that doesn't actually require any work on the developers or the users. So by having this instrument interface, it provides a very versatile but very robust and systematic view into the data. I also mentioned we can do model combinations. So this is an example also from the latest pysat ecosystem paper. But the black dots here, this is a model that's run. So we've got a range of altitudes over a full day. And then we're going to compare it to Hickomarca. So at some point during the day, Hickomarca gets turned on, right? It takes altitude profiles. So you get a whole range of altitudes. Pysat models, sorted out, hey, the red parts, this is where you have both the satellite and the model data. It's showing, this plot here showing the spatial distribution of the model data as well as the Hickomarca thing. So if you want to compare these, right, you first need to identify the data, but it's not exactly the same location. So we've got a nearest neighbor type of interpolation. So this is a satellite track here that's flying through, I believe, and you can see we're getting a stair step thing out of the model because that's the closest spatial and time location with the satellite. Or we've got things like actual full linear interpolation. So we're just trying to show some examples already included in pysat models. But the mission support is pysat lets you kind of support each stage of the mission, from the conception to proving that it works to processing the instrumentation, and then following up with science processing and outreach. So this is one of the other packages that was in the ecosystem here, pysat seasons. So this is this one will take any of these objects, it'll take any data set, and it'll do bin average seasonal results. So this is an example output from pysat seasons for the density from the IVM. So this is a logarithm of ion density in the equatorial-ish region. It's magnetic local time horizontally, right, longitude up here. And we can see we're getting a wave structure, which is typical of the equatorial regime. So what this done, I took a whole bunch of days of IVM data, binned it based on its spatial location, right? And then at the end, I took all that data and applied average to it. When I say what I really mean is pysat seasons. I just, had a function calls that do all this cool stuff for me. But it'll take ND data. It's not just one-dimensional data. And because it's built on pysat, it can iterate on all the different ways that pysat can iterate. So this one is generated daily. We've also got functions that'll say what's the occurrence fraction or the occurrence probability of something occurring. And this one is just part of the function call. I said, hey, I want you to do this one per orbit. So if you're looking for, say, like the presence of plasma bubbles, which this is looking for, changes in the background density from the background density of a certain size, aka like plasma bubbles, it can be better to look at that per orbit than necessarily per day when generating those types of, when generating occurrence statistics. So there's a whole versatile combinations of instruments and data and distributions and things like that becomes available once you have a data set that's in pysat. Then any kind of these analysis routines can use it to great effect. So my time's running out, but time is a flat circle, so the past becomes the future. pysat originated as an IDL program. So way back in the day, I called this Cindy Data Viewer. This was all in IDL in real time. And I was trying to sort out ways, how do we actually figure out what's going on with the satellite data set in a way that's convenient and works, deals with all the challenges. And this thing actually worked pretty well, and is real time. You change the things all scaled and stuff, as you watched, and with performance. But one of the core problems I found with this is once you found something cool, well, then what? Like, it was all trapped in the GUI. What are we gonna? How am I gonna do science with that now? When I started pysat, which came from this thing that I wrote, I'm designed pysat to have all the functionality needed for GUI, but at the terminal level, at the command line level. So this is the GUI that actually started it all, but all that kind of latent functionality is built into pysat, so we could lay a modern GUI on top of it for not only just for the mission, but for like public outreach and scientist outreach, right? Scientists are people too. We need easy ways to look at the data. And just here's some proof because this was written IDL. This is IDL code. I since switched to Python long ago. But at one point, Enthought had some plotting libraries out there, and they had a demo for plotting just like a two-dimensional math equation. So I took that demo and I ripped out the equation part, and I just coupled in pysat seasons, and it turned out it worked. So what you could do is you can put in your dates here for a seasonal analysis. You tell it the X data bins, your Y data bins, things like that. And I want to bin average Ryan temperature. You hit the button, in the background to do all the processing, and then just pop up a picture. And then if you moved your mouse around, you get these interfaces, these real-time plots that would show what it looked like, along the y-axis and the x-axis. So like pysat is really ready for GUIs and other things like that. It even works in other people's GUIs, but that'd be really good for outreach, but we don't have it yet. So I'm almost out of time, but a partial feature list for pysat that's super relevant. So you got the instrument objects, which I covered. It allows to generalize access to a data set. Now you've also got constellation objects, which is an arbitrary collection of instrument objects. So you can select all kinds of things together and work on them as a single group. It supports pandas and Xarray for 1D or multi-dimensional data. It's got metadata support for arbitrary standards. It's got internal logging. It's got unit testing. If you write a new instrument object for pysat, it gets testing applied to it too. So you get immediate feedback as a developer if you're doing things right. It's got all kinds of really good standards that just built into the code that help inform the way to develop for it. That makes it easier to handle very complex things. Multi-mission heritage, a whole bunch of data sets that have already been incorporated. It'll save a whole lot of time if missions and things like that would incorporate pysat rather than develop their own. And it supports missions from the conception all the way through science publications and outreach. So conclusion, pysat is perfectly suited to provide open source software foundation for GDC and future mission and science processing. The challenge right now is that there's really insufficient funding for significant open source development. So we don't have the funds, unfortunately. So, but with the GDC mission, I think there's an opportunity here for GDC to fund and contribute to open source mission software like pysat. And that would not only help GDC, but any mission coming down the line, particularly CubeSats, because CubeSats don't have the money to write their own mission processing software. Explorer missions can write their own custom stuff, but CubeSats cannot. And investments in pysat help Explorer missions as well as CubeSats. So you can have all the missions operating on the same level of technology. So I think I'm probably out of time for questions and comments, but so I'll just skip to a thank you. Thank you.
Thanks, Russell. We are over time, but if anyone has a quick question, they can go ahead.
Yeah, Russell, if you can stay for a few minutes past this, I had some questions, but
Absolutely.
Anyone else?
It sounds like no. All right, well, I will go ahead and let anyone go who wants to go. Not that you need my permission, but we will meet again in 2 weeks' time, and we'll have an overview of the adaptive project. So get excited. See y'all soon.
Yep. All right, now, Russell, I'd actually posted these in the chat, but I'm just going to read them off one by one.
Oh.
I'm going to make you the host, Shawn, because I have a meeting to run to. Thanks, Russell.
Okay. Anyway.
Yeah.
With the stuff about you have like custom cleaning code and all the pre-processing steps for different instruments. I was wondering if any instrument teams have actually like contributed code to pysat in like an open source kind of way, or if you've just written all the existing modules yourself.
I have not written all the existing instrument modules myself. So, I mean, like I did write the icon ones and, for the instrument processing, I wrote those, but While most of them are from the pysat team, we have been getting contributions from people that are not related at all. And they've, once they started, they've actually contributed more. And then the great result, at least for me personally, is when they started with this, they also have a bunch of personal or private data sets. Maybe personal is not right, besides the sets that aren't public yet. So they're also using it for their own work. So, you know, to me, that's really what pysat is kind of designed for, is to make things easier on scientists and their data. And when I get people to really try to use it, it works. So,
Yeah, no, that's promising.
yeah.
Angela?
If I could just chip in on that one.
Please.
Usually when I'm adding like a cleaning routine in pysat, I'll reach out to the PI and get their input on it. A lot of the ones in there, even if they weren't originally solicited or added by the team, like they do have input from the people in charge of the instruments, because we don't want to just put ad hoc stuff in there that's not approved by the actual people who operate the instruments.
Yeah, that's great. And also probably saves you some work, right? Like if they're verifying, did you do it right and everything, that makes sure it's correct, and it's less work for you. So it just makes sense.
Oh, yeah, absolutely. And I've never had a person that I've reached out to not be grateful that their data is, you know, going to be treated more in the way that they want it to be.
Yeah.
Yeah, it's been a positive experience there.
Great. Also, I guess this wasn't really a question, Russell, but more just a comment that you were showing off all those plugins that you had for pysat, drawing the comparison to, you know, like GarageBand plugins and things like this. And that was the first time I'd seen a few of these plugins, and also the first time I'd heard you use this analogy to, you know, the GarageBand Logic Pro plugins. So I guess the question is, what's the deal with that? Why hasn't this been more forward facing?
Well, you know, I think I have tried to use the plugin term some. Maybe it's a little bit more prevalent now because I wrote the pysat ecosystem paper, and then there's definitely some discussion among me and my co-authors about the terminology. So maybe it's just more at the forefront right now. But originally, so I had written software for GarageBand before I did my postdoc and all that stuff. And it turned out that later I was like, oh, I realized what I'd done almost like after the fact. I was like, oh, I did GarageBand, and I used all those kind of techniques in audio plugins, ended up in the pysat plugins. So
we don't host these plugins on the PyHC website, do we? I don't think we do.
I don't know.
Maybe that might seem kind of familiar.
I'd have to check. I know pysat CDF is there, but it's been kind of languishing from, you know, trying to get funding. But I'll have to check on whether or not we list all the other ones.
Are they published like in pip and conda?
Well, not in conda, but yeah, they're published just like pysat is. So they're under the pysat group on GitHub. And they all go through the same stringent process. You know, we have a lot of testing and high standards. So yeah, they all go through that.
Can I pip install them?
Yes.
Good. I mean, like from PyPI? Great. All right. Did anyone else have any questions? That's all I had. Nope. Then I guess I'm going to go ahead and turn the recording off.
Yeah. Well, thanks for staying to ask